Hello, and welcome to the newest webinar in our Radiation Safety and Wellness webinar series, Small Modular Reactors, Radiation Protection Considerations. My guest today is Joseph Zick, Health Physics Director at McMaster University and President of Senior Health Physicist Nuclear Services. Previously, Joseph has worked as Health Physicist, Health Physics Section Manager, and Radiation Protection Manager at Ontario Power Generation. He is also a registered radiation safety professional with the Canadian Radiation Protection Association and a certified health physicist with the American Board of Health Physics. With his experience in health physics, licensing, regulatory affairs, radiological waste management, and power generation, Joseph joins us today to share knowledge on small modular reactors with a focus on radiation protection. Thank you for being here with us today, Joseph. The final 20 minutes of today's webinar will be a movement break led by Xiaoming Wang of Jihong Tai Chi and Qigong in Richmond Hill, Ontario. This school is part of the Jihong Tai Chi College, which was founded in 1988 and is a large organization with campuses located primarily in Canada, China, and a few other locations. The schools are all dedicated to teaching the art of Tai Chi, with decades worth of accumulated experience and research to define and design a modern advanced set of teaching methods. Let's take a moment to go over the functionality of the Zoom meeting. We ask that during the presentation portion that the audio and video be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. Please use the chat feature for any discussions and post questions arriving from the content in the Q&A. This will help us to find your questions for the allotted Q&A portion while allowing people to have a conversation in the chat. As the webinar is only 40 minutes in length and is immediately followed by our wellness session, time may not permit for us to answer all of them during the webinar. The answers will be posted on our website along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to their professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they're being blocked by your Zoom controls, you should be able to select a different way to view the webinar in Zoom, which makes them easier to see. Today, we will be discussing small modular reactors, or SMRs. Our guest, Joseph, will speak to radiation protection in nuclear reactors and how radiation protection considerations differ for them versus traditional reactors. But first, in order to give a regulatory context, we have a short background presentation covering the nuclear reactor regulation in Canada, including information about the Canadian Nuclear Safety Commission, license classes, regulations, particularly relevant to licensing nuclear reactors, and the requirement to have a radiation protection program. We will then have the interview and question and answer session with our guest, Joseph Zick. Please note that the information today is provided at an overview level. It is not exhaustive, nor does it give legal advice. For the most part, the use of nuclear materials in Canada is regulated by the Canadian Nuclear Safety Commission, or CNSC. Examples of exceptions include military use, which is regulated by the Department of National Defence, or the Canadian Armed Forces, naturally occurring radioactive material, which is regulated by the provinces or territories, or Employment and Social Development Canada for federally regulated workplaces, as long as it is not being mined or refined for use in nuclear energy. The CNSC has 6 classes of licenses: Class 1 nuclear facilities, uranium mines and mills, waste nuclear substance activities, Class 2 nuclear facilities and prescribed equipment, dosimetry service, and nuclear substance and radiation devices. Nuclear power plants fall under Class 1 nuclear facilities. There are 4 different categories of legally binding documents for those licensed with the CNSC. The first is a Nuclear Safety and Control Act. The CNSC is established as a regulatory body under the Nuclear Safety and Control Act, a federal statute. The purpose of the Act is to protect people, the environment, and national security with respect to nuclear energy, nuclear substances, prescribed equipment, and prescribed information. There are a number of regulations under this Act. When applying for a license related to establishing or running a nuclear power plant, the applicant must detail how they will be in compliance with the General Nuclear Safety and Control Regulations, the Radiation Protection Regulations, the Class 1 Nuclear Facilities Regulations, the Cost Recoveries Fees Regulations, the Nuclear Non-Proliferation Import and Export Control Regulations, the Nuclear Security Regulations, the Nuclear Substance and Radiation Devices Regulations, and the Packaging and Transport of Nuclear Substances Regulations. Once a license is approved, its contents are legally binding. And finally, if a license holder is given an order by the Commission, it is legally binding. One set of regulations that applies to all license holders are the Radiation Protection Regulations. They are focused directly on exposures to ionizing radiation. They include the classification of workers, radiation dose limits, the requirement for dosimetry, and the identification of radioactive materials and radiation areas. One requirement of the Radiation Protection Regulations is for all license holders to have a radiation protection program. The purpose of the program is to keep the amount of radiation exposure as low as reasonably achievable, or ALARA, taking social and economic factors into account. This means that there is a requirement to keep workplace radiation doses as low as they reasonably can, not just under regulatory limits. The Radiation Protection Program, developed by the licensee, must include details about management control over work practices, personnel qualification and training, control of occupational and public exposure to radiation, and planning for unusual situations, as these are required components of planning in order to keep doses ALARA. With these aspects of radiation protection regulation in Canada in mind, we will now move to the interview of our guest, Joseph Zick. I am pleased to welcome today's interview guest. Joseph, thank you so much for being here. As I said in the introduction, Joseph has experience working as a health physicist and in radiation protection management, ranging from industry and nuclear medicine to nuclear power generation and radiological waste management. He is also the co-chair of the World Nuclear Association Radiation Protection Working Group and is a member of various technical standards committees in Canada. In these roles, he has worked with nuclear reactors for research and for small and large nuclear facilities for electrical power generation. He is currently the Health Physics Director at McMaster University, supporting the safe operation of the research reactor. Additionally, as the President of Senior Health Physics Nuclear Services, he provides consulting services regarding the safe use of nuclear technology. I'm just going to stop the share so that we appear a little bigger while we're having our conversation. So I just apologize while I do that. So, because right now I can't see anyone. So, all right, I now lost 1 second. So I just need to get my interview questions back up. So Joseph, welcome. It's nice to have you here.
Thank you. It's my pleasure to be here with you, Lynn.
Okay, so Joseph, do you mind explaining to everyone what an SMR is?
All right. Well, I guess I'll start by saying that small modular reactors, or small reactors, have existed for decades already, right? We have nuclear powered ships, we have nuclear powered submarines, and we also have the McMaster nuclear reactor, which is where I'm here today. With a 10 megawatt design capacity, it's similar to some of the small modular, minor modular reactors that a lot of organizations are currently proposing. So small reactors aren't necessarily new, and they've been and are currently being used all around the world. The part that's changed with an SMR is that is the modular component, right? It talks about how they're built. So when the McMaster nuclear reactor was built, it was built here on site, right? What the small modular reactor component brings in, it allows the reactors to really be built off-site. And then brought to a location and put together. So if you consider, coming here and having to, pour the concrete and then put it together and kind of do all of that. In this case, what we're doing is we're looking at building it at a let's say an SMR factory, putting it on trucks, bringing it to a location, putting it together, and then putting in the fuel. And so at a high level, because I could talk about this for a really long time, but I want to try and stay on time here. But at a high level, that's really the difference, right? And I really want people to understand, again, small reactors have been around for a long time, and we have experience with them. We've managed them. We understand the risks and hazards associated with them. But what's really changing here is the ability to create them elsewhere and then bring them to a location to put them together in this modular capacity. And that really helps in a lot of places where I'll maybe, if I get a chance, talk to a bit later, just when it comes to the capability to even build these in a lot of locations, right? So if you can imagine, trying to go to a community that doesn't necessarily have a local expertise in building something like this, you can build it somewhere else and bring it to them and ultimately put it together.
Okay. So how are these small modular reactors meeting different needs than the more traditional nuclear reactors?
So small modular reactors, they are designed to meet various needs, right? So obviously one of the big ones that we're looking at now is energy generation, right? So looking at being able to provide energy both pretty much from either a local perspective or even on, if you look, there's floating reactors as well, where they'll have the reactor on a ship ultimately, and then they'll take it to a community and connect it to the grid and be able to provide electricity to the grid. So that's where a lot of our focus is right now, but it's also been used again for a number of decades already when it comes to ships, when it comes to submarines. So a lot of work and a lot of experience already in these areas for use in those ways, and then also for building reactors for research and radionuclide production, which is similar to again what we have here at McMaster, which is a reactor with over 60 years of operation. That's kind of on a similar scale to a lot of SMRs. And but its focus isn't making power. We make no megawatts, don't put anything on the grid. Its focus is performing research into different nuclear materials and different ways that we can use radionuclides for to better society. And one of the major ones that McMaster is very proud of is the fact that we make radiopharmaceuticals that change the lives of people all around the world, and that's something that we're very proud of. And a lot of that capability comes from the ability to research, develop, and then support these important needs of society.
So what you're saying is, like, could the small modular reactors that people are thinking of as we bring this topic up, could they also be used for making radiopharmaceuticals?
Yeah, so there's definitely capabilities there as well that can be explored. I think a lot of the focus now is on meeting energy needs, but again, you look at the size of McMaster, it's a smaller reactor, and we're using it to do that. So there's that capability as well.
Right. Okay. So again, now why has this become a topic right now then? Like, why are they building them now?
Yeah, so again, a lot of our focus now is on building them to meet our energy needs. So for those of us like me, we live close to a big city, and I take energy for granted. Even though I worked at a nuclear power plant for a large portion of my career, I take the fact that I have electricity for whatever my needs may be, I take that for granted, right? But when we think about other communities that aren't as close to these big generating stations, so in Canada, we think of our northern communities, right? So much capability, amazing people up there, but they are challenged when it comes to energy, especially clean energy. And so a lot of their growth is really tied to the fact that they need to meet their energy needs, not only current but future energy needs, if they're going to continue to grow. And so a lot of that is currently being met with technologies that are not good for the environment. So things like diesel generators, for instance, because of the distance to some of these communities, I've heard that in some cases it takes 6 liters of diesel to get 1 liter of diesel to the community so they can use it, right? And so that's a huge expenditure from an environmental perspective. But unfortunately, their current needs, they cannot be met with hydro, right? They don't have the ability to flood areas or so on, or have the right I guess landscape to do these kind of things. There's also wind, solar, other clean technologies that don't necessarily work for the climate that some of these northern communities are in. And so they're challenged in the sense that they want to do, they want to have cleaner technology, but they don't have the capability to use a lot of the technologies that are available. So that's where SMRs are being looked at to address, these needs, right? There's, such amazing capability there, and so much opportunity for growth, but we need to be able to help them provide this cleaner energy to do so. And so that's where a lot of the SMR focus is. Having said that, that's not the only place. There's other needs as well. So when we think of developing countries, for instance, amazing, developing countries, amazing opportunities, but they are limited to their ability to generate electricity. And even if they wanted to build an SMR, they may not necessarily have, again, that local expertise to actually build a facility. And so the idea that we could build a small modular reactor at another location and then transport it to these developing countries and install them there, whether it's on ground or whether it's on a ship, whatever it may be, but be able to bring this energy to a location that may not necessarily have the infrastructure to do it themselves, is something that is really being looked at by all of the different proponents for the SMRs. And so, that's just an application that we can see for, this technology. And then even in our developed countries, there's needs there as well because of an aging or vast infrastructure when it comes to our energy distribution, right? I think we've all, gotten our electricity bills and look at the cost of how much energy we used and then what it costs for us to get that electricity to our house, right? It's a fee that you're paying no matter what, right? It doesn't matter what you're using, you're paying this kind of delivery fee, right? And so, when we're looking at that, even in developed countries, there's a significant cost associated with building electrical lines to a lot of these more remote locations that are far away from our big generating stations. And so what happens is, even if we end up building the electrical lines that will make it out to whatever this community might be, you end up getting quite a bit of loss over those lengths, right? So the further you are away from the source of your generation, the more you're going to lose. So, and the cost of, implementing or putting, these huge infrastructure systems together are also pretty significant as well. And so the idea for, especially for a community that might be further away from these generating stations, the idea that we could build something locally, again, build it offsite, transport it to this location, put it together, and then implement it is an amazing opportunity to be able to meet the needs of these communities, even in developed countries, meet the needs of these communities, and do it at a lower cost way than just trying to build more transmission lines.
So why is it that Ontario is the province in Canada where they're starting to be built?
Yeah, and I think that's a really great question, right? I'd say Canada and specifically Ontario have a long history of nuclear energy usage, very safe, long history of nuclear energy usage. And, why Ontario, I would say, is such a great place specifically for this to be done is because Ontario already has a lot of what it takes to construct and then operate one of these facilities. And I want to just take a minute to talk about what I mean by that. If I just take one of these SMRs and I put them in a community, let's say I don't know, give an example, somewhere in the middle of, the Arctic, right? And I just drop it there. It's not as easy as just putting it there, turning a switch, and then leaving it alone, right? There's a lot of things that have to go into place, right? So what do you need? First thing that you need is you can't do anything without regulatory support, right? So if we're going to use radioactive materials, whatever they might be for, whether it's an SMR, whether it's for nuclear medicine, or whether it's for research in a laboratory, we need to have a license from the regulator that allows us to do that, which means that we need to have a regulator that actually has the expertise to oversee whatever this technology is. And we're very fortunate in Canada that, the Canadian Nuclear Safety Commission and, Atomic Energy before that, we have decades of really good regulatory oversight and support in Canada. And so having a regulator like that, where this isn't a whole new concept for them, but they already do, higher risk things like our full, large nuclear power plants like PG and Bruce Power, they already have that expertise. And so that makes Canada a really good place in the sense that, we have a regulator that already has a lot of the expertise. Now they're gonna have to look at this usage specifically and make sure that they're comfortable with it and so on, and that they have the expertise expertise to look at that as well. But having said that, we're fortunate to have a regulator that already has a lot of expertise and is internationally recognized for their regulatory oversight and support. So that's the first part, right? Can't do anything without that regulatory support. Then from there, when we look at the ability to design a facility like this. We're very fortunate in Ontario and Canada. We have a number of organizations, great engineering firms. I'm not going to name them all here because I'll get in trouble for missing one, but we have some amazing engineering firms in Canada with some amazing experience, scientists, engineers, people that can help design these facilities and design the programs to support them to ensure that they can be operated safely and that we can demonstrate to that regulator that we can operate these systems safely or these facilities safely. Another really key important part is supply chain. And so, one of the things for any big construction projects is, where are you going to get all your materials, right? How are you going to put all this together? There's some very specific things that we need here. And so being able to have a good supply chain that will meet the needs for actually building these SMRs and also building the local infrastructure required to support the SMRs as well is a key part of making this successful. And Ontario and Canada has demonstrated that we have a really great supply chain, especially our nuclear supply chain, right? We're very fortunate that, we already have a really good nuclear supply chain that supports our major, large nuclear facilities, and we can count on that same supply chain to help us get the materials and different things we need to build an SMR as well. In addition to that is the ability to construct. I think Ontario, Canada, we've demonstrated that we have the ability to take on these very large projects and see them through to completion, right? So obviously in the nuclear side of things, we have the refurbishment projects that are going on at Darlington and Bruce Power, these are massive projects, take amazing project management, take a lot of people, qualified staff, training programs. Huge amount of effort goes into doing these projects, and Canada and Ontario have demonstrated that we have the ability and the people to do this kind of work and do it safely, right? And I was sorry, a little off topic, but my son had a project about the CN Tower the other day, right? And so we went to the CN Tower as part of his project, and I took my dad, and my dad said he came to Canada in '67, and when he came, the largest building in I think the largest building in Ontario was actually here in Hamilton. It's a big concrete building here in Hamilton, and the CN Tower didn't exist at the time, right? And my son just couldn't believe it because he just can't imagine Toronto without the CN Tower there, right? And the CN Tower was built as a really, for a lot of reasons, obviously communications and so on, but it was really just to show the strength of Canada's infrastructure to do these kind of projects, right? And so we do have that capability. We've taken, in Canada, we've shown that we can take on these big projects. We can build nuclear power plants, we can build CN Tower, we can build things, and we have the people to do it with great experience. So that also is why, doing this in Ontario is important. And then the last thing, sorry, I'm taking too long on this question, but the last thing is the support. After you build it, it doesn't stop there, right? The regulator continues to regulate and ensure safety. The operator continues having to do all sorts of different safety checks and all sorts of different things to demonstrate, that they can operate safely to themselves, right? And then also to obviously to the public and the regulator and so on, right? So there's a lot of infrastructure that you need in place to build an SMR, and I think that Ontario is the right place for us to be able to do this. And I think that's why a lot of the focus is Ontario, because we have a lot of this infrastructure and the support already in place to be able to do this safely. Sorry, took way too long on that.
That's okay. So here at the Institute, we are our purpose is to provide people with information, right? Like we don't pick sides one way or the other with topics like this, but our focus is radiation protection. So I guess in the last two questions are really getting to our focus on radiation protection. So the big one, how does this radiological risk change from a nuclear power plant to when you're going to a small modular reactor?
Yeah, it's a great question. And that's really the question that any radiation safety person should be looking at. And I'd say any radiation, when we look at anything from a radiation safety perspective, everything when it comes from a program perspective always comes down to what we call as the source term, right? So what is the radioactive material that you have present? How is it going to change as you're using it? And how are you going to keep people safe from it? But you need to understand the radionuclides to understand the risk and so on. And so really when we look at the differences between a nuclear power plant and a small modular reactor, that's what it really comes down to, is that source term difference. And so For example, my program for the use of a small source or radiation device at a laboratory here at McMaster for research is going to be very different than my program for a nuclear medicine department at a hospital or for a nuclear power plant, whether it be an SMR or a large nuclear power plant. And so really it comes down to this source term and understanding the source term differences. And so when we look at a nuclear power plant that's generating 1,000 megawatts, right? The core of that reactor is much larger, right? So thousands of fuel bundles, much larger source term. So inventory of radioactive material is much larger. When you instead compare that to a small modular reactor, the source term changes, right? So you have a much smaller reactor core. Now, having said that, there are still things that are different there, right? A lot of the small modular reactors are using either low enriched uranium or high enriched uranium, as opposed to our CANDU reactors, which use natural uranium, right? So again, differences in source term, and our programs need to account for that, right? So we need to understand that, what are the radionuclides that are there? How are they going to be expressed when it comes to the actual work environment? So what kind of, starting with the workers at these locations, what kind of hazards are going to be present there? And really that's not different than a large nuclear power plant or a small nuclear power plant, right? We're going to do the same thing, right? What kind of hazards are there? What kind of levels do we expect to see? And how are we going to keep workers safe? Similarly, based on the operation, what do we expect our releases to be? And then based on that source term, understand what our releases are going to be and how are we going to demonstrate that we can properly measure those releases. How are we going to demonstrate that we can minimize those releases to ensure that we're keeping them as low as reasonably achievable, social and economic factors considered, of course. And then how are we going to minimize any impact on the public? How are we going to minimize our waste and all these kind of things, right? So our program ends up having to look at all of these things, but it's all tied back to the source term. And so it's important for us to understand what the source term is, what radionuclides are going to be there, how they're going to be, released to the various environments, and then we'll build our programs to actually address those source terms.
And like for different types, there's more than one type of small modular reactor, right? So the source terms can be different for different types, I assume.
Absolutely, yeah. Source term is going to be very different, right? So if you think about like a micro modular reactor, which is kind of something more similar to what we have here at McMaster for our McMaster nuclear reactor, you're going to have a very small core, right? But again, you need to consider that it's going to be either lower enriched uranium that you're dealing with, or LEU or HEU, low enriched uranium or high enriched uranium that you're dealing with, depending on the design. For larger small modular reactors, again, you're going to have a larger core, which means you have a higher potential for releases, and the magnitude of those releases will be potentially higher as well.
Okay, and so from this, how would a radiation protection program be different between a more traditional nuclear power plant and a small modular reactor?
Yeah, and that's I guess what I kind of started saying in the previous question too, is that after we identify our source term, then it comes to implementing our program. And from a program perspective, they really aren't that different, in the sense that our program needs to meet regulatory requirements, right? The CNSC, the regulations are clear, right? If you're going to use radioactive material, here's the limits that you need to stay within. Here are the objectives that you need to meet. Here's the dosimetry requirements. Here's the all of that is already very clear. And so from a program perspective, we still need to have those same components to control the hazard, right? We need to protect people, whether it's our staff performing work at the location or people outside of the location, the public. We need to be able to demonstrate that we can, minimize our releases, and that we're considering the environment and any potential releases to the environment. All of these controls are already in place, which again is why doing this Ontario is so nice, because we already have good regulations. We already have a good regulator. We've already been given what the sandbox is for us to be able to demonstrate good compliance. And so what we need to do from a program perspective, whether it's an SMR or a large reactor or even a nuclear medicine department, is we need to have a program that says, I've looked and I've recognized that this is my source term. Based on my design, I recognize that these are the hazards that are going to be present. And then, here's how they're either going to be controlled, or if there's any releases, how they're going to be measured and quantified to demonstrate that they are below our regulatory limits. And that's really, a key part of it, right? So just because the reactor is smaller doesn't mean that our program doesn't need to be just as robust to meet regulatory and program demands, right? And so what is different is really what it takes to implement that program. So for instance, a large nuclear power plant, can-do facility is complex, right? A lot of different moving parts, a lot of things that have to be inspected, maintained, changed, operated, and so on. And so because of that, you need a large organization of people to actually do this work. And because you have that large organization, you can compartmentalize, right? So you can say, all right, I'm going to have a mechanic, and that mechanic is going to fix my pumps. But that mechanic, I'm not going to train him to be a radiation technician because I have radiation technicians. So that mechanic, he's going to fix pumps that are clean. And if he needs to fix a pump that's radioactive, a radiation protection technician is going to go with them and help them with their radiation safety. So from a program perspective, you're still taking care of radiation safety, but you have two people doing a job. And there's enough work that you can justify having those people. At a small modular reactor, you don't necessarily have as much work, especially with the fact that we have, decades of operating experience now. We found smarter ways to do things. And because of that, you don't necessarily need as many people, and you don't need there aren't as many things to fix in a lot of these small modular reactors. The design is very simple. And so you don't need this large workforce of people. You actually don't even have work for them, even if you had, right? So now that the workforce is smaller, you can have a mechanic that's also a radiation protection technician. And now you will train them on both things. They will still be, trained, qualified, and capable to go and do that within the program, but it's going to be done by one person instead of two. Right. And that's something that, especially in Ontario, again, that I think, we've already demonstrated that we can do this safely at our nuclear power plants. So, a lot of, when I was at the RP manager at one of the nuclear power plants, there was more radiation protection qualified people that worked for operations and maintenance than that worked for my department as the radiation protection manager, right? And they were amazing. They were people, especially, some of the older experienced folks, like they, an operator that are trained in radiation safety, but also knows the station will recognize things better than someone that's just trained in radiation safety, right? And so, having this combined training capability is really important. And so we've demonstrated that we can do that safely at the nuclear power plants. We've also demonstrated that we can do that safely here at McMaster. The operations staff that run the reactor here, they take care of their own radiological safety. They do their own measurements. They document their own measurement results. They are amazing at implementing the radiation protection program. And so in Canada, again, in Ontario, because we already demonstrated this, I think it also, again, puts us in a good place to be able to say that, we have demonstrated capability and good programs and good training to train people to safely work with radioactive material, even if that person has more than just kind of that one task. And that's where I see a lot of the differences in our program from, some of our larger stations to this, is that it's really going to come down to how it's implemented. So again, the regulations won't change. They are what they are. This is what safe operation is, and this is what the regulatory expectation is. That's not changing. What we need to do is to demonstrate for a smaller reactor how we're still going to meet all of those different regulatory needs. And there's been some pretty, amazing and innovative ways to do that. So for instance, right now, if I want to do radiological surveys or to demonstrate that, I'm measuring the radiological hazards in an area, I will send a radiation technician, and they will go into each one of these areas, and they're going to take measurements and then come back, document the measurements in our database, and then we'll review them to make sure that they meet our expectations. And that's great. That's what the program needs to be able to do. Again, we need to demonstrate to ourselves that our work area is safe and within what we expect it to be. But it involves someone taking the time to do that, right? If in a lot of the new small modular reactors, a lot of this monitoring is going to be done in real time, right? So they'll have a radiation monitor put in each one of these locations that will be connected to the control room, and the control room can monitor this equipment and see, and we can, have automatic, trip set points, alarm set points, warning set points, whatever we decide from a program perspective, and they will be able to automatically see what's going on, right? So as opposed to waiting for someone to go do a survey to say, oh, I think there might be something in this room, they'll know right away, right? So we've learned a lot over decades of experience to say that we can better implement this, and it's being done as part of the design. I don't want to say that it's not being done at nuclear power plants currently. There's been some amazing changes and innovation and stuff there. It's just that they're doing it after as part of the SMRs. We're doing it right at the beginning, right? We're including it in the program, so that way you have that capability. Having said that, though, it also introduces challenges, right? So if you think about a real-time monitor, it sounds great as long as it's working, right? But how do you know it's not working? And how do you make it a smart instrument so that when it's not transmitting, they know it's not transmitting, and they don't just keep seeing the same result even though something's changing, right?
Yeah.
Again, there's a lot of good technology that's already in place there, that will be put into use, but a lot of that again is all just coming into our design of our facility. So anyway, I could keep going. I realize I only got 5 minutes, so I'll stop.
Nobody's put any questions in the Q&A. Okay. I don't know if anybody. I have tons, but I could sit and talk to you all day. But is there anyone that has a burning questions? We have about 5 minutes left before we go to break. Or sorry, to wellness break, because I have one I will ask if there's none there, just because there's nobody talking in the chat and there's nobody in the Q&A. We have a quiet group today. Okay, so a question that we've gotten from the chat: what does a typical outage schedule look like for an SMR?
So that's a good question, and a lot of it, again, I'm the RP expert, not necessarily the maintenance expert. I'll just tell you what I have seen. So a lot of it is going to be similar. You're going to see that you're going to have outages or shutdowns that take place on a routine frequency. At this point, you're looking at every 2 to 3 years. A lot of the shutdowns are based on inspections. So, not necessarily that you have to replace something. Most of the components on these small modular reactors are being built so that they don't have to be changed as part of the entire cycle, right? So you're making equipment that's going to last 20 years for the whole cycle of your facility. Having said that, you still have to plan that they're going to break down and those kind of things. So there's a lot of inspections that are taking place, and ultimately you're going to have these shutdowns that are going to do those inspections. You're going to do any maintenance that you have to do, but again, a lot of the design for these facilities is being done so that you can minimize those shutdowns. And the actual shutdowns themselves, they're really not lasting kind of what, for nuclear power plants, again, much more complex. Shutdowns are usually on the order of weeks or even months. A lot of the SMR shutdowns are really on the order of like days to weeks for how long it's going to take to do the work.
Okay, so I'm just looking in the Q&A. People that have typed their questions in the chat, do you mind throwing it over in the Q&A, just because there's discussion going on and the Q&A is easier to follow if it's just for the questions. And what are the challenges you expect an RP from using an SMR that uses a different reactor technology? So the BWR instead of CANDU. So like with the CANDU, you're using natural uranium, and I assume the questions now you're looking at enriched.
Well, you're using enriched. Also, I mean, you probably can't get more different in technology between a BWR and a CANDU. It's very, very different in the sense that design is different. Like for instance, like if I understand right, I think your turbine side is actually contaminated in the BWR, right, versus CANDU. Whereas CANDU, for instance, tritium makes up a relatively large component of your source term and something you have to manage. In a BWR, it's there, but not the same source term. And that's, again, kind of where you really have to focus on your source term to understand, what is it going to be based on your modeling of your core and releases from that core. I saw one of the questions that was in there as it was around what radionuclides are going to be there. What you're going to find is that they're very similar, right? The same kind of radionuclides that you would expect to see at a nuclear power plant, you're going to see here as well. Again, the ratio is going to change, but a lot of the main ones, so like your argon 41 which really comes from activation of air, and then your radioiodines, which comes from the fuel itself. So a lot of the radionuclides that you see are very similar. It's just the ratios that changes. Sorry,
okay, yeah, sure. I think we're going to run out of time for all the questions, and it seems like some people can't access the Q&A, so I'll try to go back and forth. Just can you comment on training for staff, bringing nuclear technology to remote areas of Canada? This is the question I wanted to ask. Would the implementation of an SMR in an area like this attract more trained individuals to the area, or is it possible to implement training with an existing community already? And I'm from a rural part of Canada originally, so to me, it's like, how do you get this was exactly the question I was going to ask myself. So.
And I think, this is definitely the question that we're hearing from communities as well, right? The communities want to be able to own and operate, right? And so, I think there's definitely a lot of capability when it comes to, like, Ontario. Yeah, we have a lot of experience in training people, right? And so we have the capability, I think, and good programs in place to train people. Having said that, there is a certain base knowledge that's required, right? So I can't necessarily, at a nuclear power plant, train someone to be a scientist or an engineer, or some certain kind of base understanding that you need. Having said that, though, if you do within these local communities have people that someone that's engineer, and now you're teaching them some of the nuclear side, I think that capability is there. From an operations perspective, I think that there's definitely a lot of good programs and good experience from our nuclear plants and other nuclear facilities of bringing people in with certain minimum under qualifications, and then training them to be operators. A lot of the people I worked with at OPG that were in operations were people that did not, they didn't go to university for this kind of thing or college for this kind of thing, but they came in, they got trained up. It's a very robust program. And we also have to demonstrate again to the regulator that before we let somebody do that, that we have actually provided them with the training that makes them not only trained but competent. And they need to demonstrate that not only through the sitting in a classroom, but also through demonstration, through oversight, through different field experience as well before we can call them qualified. But I do think, just in short, that there's a lot of capability and a lot of opportunity for local communities to do a significant portion of the work at some of these SMRs.
Okay, I know that maybe we'll just there's two more if we can be quick on them. Hopefully just an extra 5 minutes won't be a problem. How will contamination surveys change?
How will contamination surveys change? I would say that they wouldn't change much at all, right? Same idea, right? You're gonna have to go in, you're gonna take your large area wipes, you're gonna take your swipes to quantify how much is there, but it's gonna be the same thing. It's just gonna be making sure that you're adequately measuring the radionuclides that are making up part of your source.
Actually, we've got another one here. Would a large city such as Toronto be serviced by one SMR? And would the concerns of a catastrophic incident be as warranted with an SMR?
So I can't say I'm the expert as to how much energy you would need to support a large city like Toronto. I've seen SMRs of various sizes. So, could an SMR be used for a relatively large city? I would say yes. Having said that, in your concern of a catastrophic incident, I would say that's probably one of the areas of biggest learning and OpEx and design change when it comes to these reactors. And I could talk about this for a really long time, but the reactors are getting to the point where, as opposed to having these large exclusion zones, we can, because of their design, make a very small exclusion zone, which ultimately means that there's a less chance of a release that's going to impact a large area of around the reactor. And so I'll have to leave it at that here. Don't have too much time, but definitely a smaller impact associated with an SMR.
Okay, thanks. And I think there was and a question about molten salt. Why do molten salt type SMRs seem to be a bit more controversial in terms of their efficacy? But this is getting away from radiation protection, right, into more. I don't know if you just have 2 minutes to make a comment on that.
Yeah, so like I said, I can't say that I'm the expert to speak to the molten salt. All I can say is that the technology itself, from a rad safety perspective, it's a similar thing that you're dealing. I mean, you're ultimately working from a physical perspective. It's liquid rock, right? But from a program perspective, you still need to be able to demonstrate that you can measure the hazards that you have, and that those hazards associated with this are below our program and regulatory limits.
Okay. Well, thanks so much, Joseph. We really appreciate your expertise, your ability to communicate well in a very short amount of time and answer these questions. And just for people to know that here at the Institute, we thank Joseph for his time. If you do have questions about this or any other radiation protection, whether it's ionizing or non-ionizing, that the Institute is a not-for-profit, and that's our purpose, is to get the information out there, not to say one way or the other, but it's about the radiation protection aspects. I will go through afterwards and look and see if there's any other questions that are there that we weren't able to answer, and between Joseph and our staff that we will post them. But very much, we do appreciate your time today. And I typically put up how people can get in touch with us. So I may just share that before you go. So while I'm doing that, Joseph, if you would like to say goodbye, that-
Yeah, no problem. So again, thank you for having me. It's a great topic. I know a number of people on this call, and I think you know I consider myself a radiation safety nerd. So I really enjoy this topic. But more importantly, you know, it takes specific kind of people to ensure that you know we can keep people safe from these new nuclear technologies. Some amazing things that we can do, right? We can make radiopharmaceuticals, we can make power, we can do so many things. But from an RP perspective, our job isn't necessarily that. Our job is to how do we keep people safe, right? So we
Yeah.
can maximize that benefit, ensure safety, and that's not going to change. Doesn't matter what we're talking about, whether it's nuclear power or whether it's anything else, right? So that's what we need to be focused on. But I do believe that we have that expertise here in Ontario, and that's why it's been such a focus for us when it comes to SMRs. And I'm looking forward to what the future has in store. So anyway, thank you very much.
Thanks so much, Joseph, and I hope you have time to read the comments because you're getting a lot of thank yous there. And with that, I'm going to, so if people do need to get in touch with us or have any questions, there's our 1-800 number and our email address. You can send them along and we will help. If we don't know the answer, we do have consultants and other people in our realm that we can ask and track down some support for you. So with that, we're going to move to Charmaine Wong, and she's back with us today to be able to help with our Tai Chi, our wellness break. She is from Zhihong Tai Chi and Kijong in Richmond Hill, Ontario. So I just have to share the sound, Charmaine. I'll be right. I will get that. I think you have two separate chat. I think you're right at the bottom with Zoom when you don't. There we are. Okay.
All right.
All right, Charmaine. I think I can hear you.
Okay, here. Yeah. All right. So yes, can you hear me now?
Yes, we can. And we do realize that not everybody can stay past the lunchtime, like, but we do encourage you if you can participate, that it's great to have the ability to work around this and then go back to work. So I'll move it over to you, Charmaine.
All right. Thank you, Lynn. I'm happy to be back here again. So what we're going to do today is to continue to practice the moves that we learned in the past lessons and continue to build on them by learning some additional nuances behind these moves, as well as some Tai Chi principles behind them. All right, so before we get going again, let's do some warm-up exercises, and that would help us get off our chairs, all right? So let's start with the first one. They're gonna be the same as last time. If you have attended the previous lessons before, then you know what we're gonna do right now. So if you can stand up tall with your feet shoulder width apart, all right? So the first move that we're gonna do is just to, if you can interlace your fingers, place them underneath your belly button, all right? And then you can just bring the hands up. And as you stretch your arms up and press the palms towards the ceiling, you want to stand up tall and look up to your hands. Then you can look back to the front, relax your arms, release your fingers, and bring them down with a slight semi-squat. And then you can repeat that again. And as you stretch up, you can breathe in. You look to the front again, and as you come down, you can breathe out. Let's repeat that again. Go up. Stretch and breathe in. Relax and breathe out. Now let's try that one more time. Breathe in deep. As you look up. And as you look back to the front and open your arms, breathe out slowly. One last time. Stretch up, look up, breathe in. Look to the front, slowly breathe out, sit down a little, and bring your arms back down. All right, just relax a little. So now we're gonna go on to our second warm-up exercise, which is one of the basic exercises that we would do for practicing Tai Chi, all right? Now again, have your feet shoulder width apart. Now we first raise our arms on the sides with the palms still facing down, not completely in a straight line, but slightly forward in a big V shape. As you raise your arms to the top, you place the palms facing each other, and you draw the shoulders and elbows down while you do a semi squat. You continue to lower our arms as we stand back up. And then let's do that again. As you stretch out, don't lock your elbows. You want to be expanded, but you want to keep your arms slightly relaxed. And then you go down and draw the arms down. And you continue to let your arms go down as you stand back up. Let's do that a couple more times. Sit down, relax your shoulders and elbows, and continue to bring the hands down. And let's just do that one last time. Sit down. We call it sitting down because we want to hinge at the hip joint, all right, which we're going to explain a little bit more onto our next moves. All right, now, so again, relax a little. Now we're going to do the first Tai Chi move that we learned in a class. If you remember, the name is called cloud hands. Now we have to have a little bit of space going sideways. All right, so you can find some space. I'm going to start with going to this side. If I'm your mirror image, then which means you can go to your right side, right? Now, again, you can start off with the feet shoulder width apart, maybe slightly further apart. And then when we start the cloud hands, we are going this direction. So this arm has to be a higher arm. The other arm with the palm facing down, you place it slightly to the side of your body or in front of your body. All right, and then we can get going. We are stepping sideways, if you can remember. Let's just start your stepping your right foot to the right side. And then we move our weight entirely to your right leg. We're going to switch the arms. So your left arm would go up, your right arm would go down, and you would bring the feet closer together, but still at shoulder width apart. And then we're going to move to your left side. Repeating that, we're going to switch our hands and step sideways. We're going to switch our hands and step your left foot back closer to the right foot and move the weight. Switch hands, step, move the weight. Switch hands, step, and move the weight. Now, if you have space, let's just do one more time. Switch your hands, step, and move the weight. Switch your hands, step, and then as we finish, we can move back in the middle. All right. Now, we're going to add a couple of more requirements to this move. And I'm going to split that into upper body and lower body. And not to pile everything onto you, I'm just going to add one additional requirement to the upper body and one to the lower body. All right. Now, what we're going to do with, let's start with the lower body, right? So when we're stepping sideways, as I told you before, we should be going slow. But when we are moving towards one direction, I would like you to slightly increase your turning of the hip so that this hip joint can be properly bent. What we don't want to do in what we call a horse stance, when you're kind of like riding a horse, is that you bend only with your knees. That is how it's going to look like if you just bend with your knees. What I would like you to do is you push the hip slightly back so that you also bend at the hip joint. So that's why sometimes we call this sitting down. And in order to be able to sit down properly when our weight is on one leg, it's easier if we slightly turn the hip. If we are very square to the front, it's very difficult to really close this hip joint or bend this hip joint. All right, so that's the idea. All right, let's just practice one more time with just focus on how we can improve on our lower body. All right, let's just say we go back this direction. Okay, now this time we start with sitting down a little bit, bending the hip joint. We're going this direction, so this arm is a higher one. All right, now, and then we step and move our weight to your left side. Now here we want to turn the hip a little bit more so that we can really close that hip joint. Switch your hands and place the right foot back closer to the left foot. Now we're going to move the weight to your right side. And again, the hips slightly turn to the right. As we switch hands and step, we move our weight to our left, to your left, and then you turn slightly more to the left. Switch hands, step. Move to the weight to the right and slightly turn to the right. Switch hands and step. Slightly turn towards your left, switch hands and step. All right. All right. I don't know if you find it a little bit more challenging because we require a little bit more of a stronger lower body, and that's how we strengthen our legs. All right. Now, in terms of the upper body, one requirement is just that we want to feel that the whole arm is relaxed and rounded. We call it an arm bowl. So we don't want the elbows to be really bent. We don't want our shoulders to rise. And we don't want to lock our elbows, especially the lower arm, because you're stretching it out. We don't want it to be straightened and locked like that. We want both the upper arm and the lower arm to form a really smooth semicircle. All right, now let's try that again, going this direction. Now, this time you have two things that you want to pay attention to: arm bows, as well as the turning of the hip joint in order to close the hip, right? By turning the hip in order to close the hip joints. All right, so let's just start again going this direction. Feet a bit wider than shoulder width apart. This time we are going to have this arm up because we're going this direction. Make sure that both arms are semicircles, right? This rounded. Right, and then we're gonna get going. Step, move. The arms don't really move as you move your weight. Now your weight is on your right foot. Make sure the hip is slightly turned towards that direction as you move the other leg closer. And then you go back. Make sure that the hip is turned, and then you switch your hands and step again. And those of you, if there are any one of you who is new to Tai Chi, Tai Chi is always practiced in a slow manner, not because we're not capable to move fast, it's because we want to really pay attention to all the details. Okay, one last time, switch hands and step. Okay, all right. Now let's move on to the second move that we learned from before. Now the next one, if you remember, is the parting of the horse mane. That one is a little bit more challenging with the footwork. So before we actually do the moves, we're going to practice the footwork again. All right. Now let's just do an overall review to do together. We need to move forward with a sequence of bow steps. All right. So hopefully you remember what we did from last time. And we're gonna try to do it together. Now without the arms, so you can put your hands on the hip, all right? And then let's just start with turning, let's say the right toes to 45 degrees. And then the other foot, we're gonna put down in front and then move the weight to the front leg. A bow step means that most of the weight is on the front leg with the toes pointing forward and the back foot pointed 45 degrees out. And to take the second step, we shift our weight back to free up the front toes, turn the front toes out, and step the other foot forward with the toes pointing forward and move the weight, most of the weight to the front leg. Let's do that a couple more times. Sit back and turn. Move the weight to the front foot, place the other foot in front, and then move the weight to that foot. Let's just do one last time. Sit back and turn out 45 degrees. Move the weight. Place the heel forward. Move the weight to the front. All right, now with that, we're gonna try to add a bit more requirements to this footwork, all right? Now, we talked about the closing of the hip. So what we're gonna do in this case with the bow step is that when we turn and place our weight entirely on that supporting leg, we also wanna make sure that that hip joint is bent like this. And in order to have what we call alignment of the whole body, not just the hip needs to be turned, your shoulder needs to be slightly turned as well. Otherwise, if my hip is turned this direction and my body is facing this direction, my spine is twisted. So you don't want to have that happening. So you need to also turn the shoulders so that everything is aligned to this direction, all right? And then when you step the foot forward, you want to keep that alignment, right? We call this an empty step because the right foot has all the weight and the other foot basically has minimal weight until you are ready to move, then you go forward. And again, because of that, we do this very slowly. All right, now let's just do that one more time together and we'll add our hands. Turn the right foot. Now make sure your hip is turned towards that direction as well as your shoulders. And then as you place the other foot forward in an empty step, this foot is basically empty, then we're going to move forward. And then now we can square to the front. Let's do that one more time, a couple more times. Sit back, turn the front toes and hip and shoulders. Then as you put the weight forward, not the weight, the heel forward, the weight is still primarily kept on the back foot. Then you can slowly move towards that front foot and sway. Let's do it again. Sit back, turn, turning the hip, turning the shoulders. Make sure the hip joint is bent. Put down the heel without shifting weight yet. When you're ready, you shift weight and squaring to the front. All right. Now, with the footwork practice, let's add the arms. All right. Let's do a quick review. The arms, there's not a lot of additional requirements from what we have just talked about, but then let's just review what it looks like. All right. So after you turn to the right side, we have a right hold ball to start, which means your right hand is on top of your left hand, as if holding a big ball, palms facing each other. And then you place the other foot forward. And as you move the weight to the front, we spread the arms diagonally, right? So the lower arm becomes the upper arm and vice versa. And then you do the second step, focusing on the footwork first, turning the toes to the left, to the front foot, turn the hip, turn the shoulders. And then you have a left hold ball with the left hand on top, stepping the other foot forward. And then as you move the weight, you spread the arms diagonally. Let's do that again. Sit back and turn. Move the weight to the front foot, right whole ball, or the whole ball of that arm on top of the other. Put the foot forward and spread the arms. All right. Now, in terms of the arms, what are the requirements? Arm bows again. What that means in this move is that when you stretch your arm forward, like in the very last time we did it, we don't want to lock our elbows, so we don't want to straighten our arm like that. We want to have it slightly curved, but still extended. The other arm, the more important one, is that when you spread your arms like that, you put this arm down and not really pull the arm too far back, because that would not be a semicircle anymore. The semicircle from the middle of the back all the way to the hand goes in a semicircle only if you place this hand, this arm with the elbow in front of the body. So when you have a whole ball and spread diagonally, this lower arm, you don't want to pull it back too far. All right, now let's try that again. This time with the arms, adding the requirements. All right, now turn. Let's say turning your right toes. Body turn, shoulder turn, right whole ball. The other foot step forward. As you move forward, you spread your arms, and let's just check the two arm bows. Again, the second time, sit back, turn front toes, turning the body, turning the shoulder, left whole ball. Place down the heel. As you move forward, you spread the arms, and two good arm bows. Again, turn the right foot, right whole ball. Place the other foot forward and spread the arms. Then just do one last time. Sit back, turn, left whole ball, place the other foot forward, spread the arms diagonally, but remember your arm bows. All right. I guess that's in the time that we have for today. So hopefully we'll have another session again, then we can have more practice on these movements. But before we go, I just like you to have a really quick cool down exercise. All right, so just a few movements. Again, standing with your feet shoulder width apart. Let's bring the palms up, breathe in. Turn the palms back down and breathe out. It slows down your heart rate and calms your breath. One more time. Breathe in. Breathe out. And last time. Breathe in. Breathe out. Okay. All right, so again, thank you for having me back here. So I'll turn it back over to Lynn.
Hey, thanks so much, Charmaine, and we do appreciate you being here. I think it's a great way to continue on with our afternoon. And I will be sending out information to everyone that signed up, whether they were able to attend or not. So if you want to know more about Charmaine and the Tai Chi School, it will be there in that email. So thank you again, and thanks to everyone who was able to stay. We appreciate you being here and supporting the Institute. Thank you.